In my last video, I went into Odin's reflection. It's a simple way to look at your types at runtime, great for stuff like serialization. Sometimes though, you need to dig a little bit deeper into your program. For example, you may want some process to analyze code, perhaps for generating bindings, or doing some diagnostics, or in my case, syntax highlighting. For that, you need to actually inspect the parsed program in a structured form, called an AST. Thankfully, Odin provides a tool for this right out of the box, inside the core library. Core Odin is a small collection of packages for tokenizing, parsing, and analyzing the AST of an Odin program. The easiest way to get started is with parser.parsefile. First, you'll declare a parser and a file. The parser doesn't need any initialization, but the file does. At first, it looks like the struct is stupidly complex, but it's actually really basic. All of this is going to get filled out by the parser. The only thing we need to set is the actual source code, as well as the file path. We'll also set the derive field to point to itself, which isn't necessary, but makes walking the AST a lot easier later on. Now, you call the proc, and you're good. Congratulations, you successfully parsed Odin source code into an AST, and now you're ready to start screwing with it. One thing that's worth mentioning is that there's currently no way to forward this AST into the Odin compiler, which means it's not very useful to add or remove AST nodes usually. You could write your library as a full build system that takes the code, uses AST stuff to process it, and then turns it back into different source code to feed into the compiler, but I wouldn't recommend it. It's a very complicated system, and it screws up things like source code locations. You're usually better off not trying to hack the system and just using normal Odin code. For this demo, I'll be making a special noPointer attribute, which we can attach to a type. Then, this code will yell at us anywhere that we use the type inside a pointer. For simplicity, we're going to be going over the code in one pass, which means this won't work for any code where the type is used before its declaration. This is also only for one file, but it's not too difficult to use it on multiple files. You basically just need to store some extra state and use the file walker in the new OS package. So, we'll start by parsing our code into an AST like before, and call in a new walk AST procedure. Odin provides AST walking functionality for us, but the process is a little bit interesting. The AST package has a walk proc, but it gets a little bit weird. It needs a visitor and a node. We'll set up the visitor in a second, but let's just pass that in for now, alongside our file. Now, on to that visitor. First, it needs a procedure. For simplicity, I'm just defining this inline here. The procedure has a slightly odd signature, particularly with the return type. You see, after every node, we have to return the visitor again. When we return nil, that's the end of the walk. In theory, we could actually switch visitors in the middle of our walk, but I haven't found a great use case for that, especially because the walker doesn't tell us when we exit a node, only when we enter. Because of that, we're just returning the same visitor directly. This means we'll always walk the whole tree. In here, we'll call a little process node procedure that's going to do the real work. There's also the data field, which is how we pass information into the visitor, since Odin doesn't do closures. For simplicity here, I'll just use the global variables anyway, since that's really not a big deal. I assume you're familiar enough with passing information through raw pointers to do it yourself if you need to. So, what happens inside process node? First, we need a nil check. There are cases where the walker will pass a nil node here, and we need to immediately ignore those. Next, and most importantly, we need to figure out what type of node we're actually working with. The structure of the nodes is a bit confusing, and it's somewhat recursive since nodes point to themselves, but it's okay. There's a derive field that tells us exactly what type of node this is. It's a union, so we'll do a type switch, and there are actually a ton of cases to cover. This union has more than 80 variants. Thankfully, we only care about one right now. I have a project where I actually care about every single variant, and it is a stupidly large switch statement. For us, though, we only care about value decal, since that's what we're checking. Value decal stores some extra info on it, including those attributes. Unfortunately, the process for checking the attributes is a bit of a nightmare. First, we loop over all the attributes. Then, we loop over each attribute's elements. From there, we can check if this element is just an identifier, and then we can check the name. I'm going to pull this out into a separate proc, since that's just hard to read. Now, we only care about this node if it's a struct declaration. So how do we check that? Well, that's part of the declaration as well. Because Odin supports multi-value declarations like this one, we have to figure out what we're doing with it. For simplicity, I'm just going to only support single value declarations here, because honestly, when have you ever seen someone declare multiple types in one expression? It just doesn't happen, so I'm comfortable crashing here. Now that we know there's only one value, let's check to see if it's a struct. If it's not a struct, I'll do another panic. Of course, you'd want better error handling here for your own program, and maybe even support for other types, but not here. Otherwise, we're actually good to go. We've ensured that the type has the right attributes and that it's applied to a struct, so we can save the name of the struct in our little table of no pointer types and move on. Next up, we need to actually find these pointer types. First, what types do we actually care about? Well, we need pointers and multi-pointers, and we'll also disallow slices and dynamic arrays. We won't be running deep recursive checks for simplicity, so let's just write these 4 cases. Starting with basic pointers, we need to see if the element is an identifier, and if that identifier is in our list. If so, we'll just print a little error about it and move on. I'm going to put that error into its own procedure so that we can make sure it's consistent across all of our types. Now, we can copy this down for multi-pointers and dynamic arrays. Slices need a bit more handling since, for whatever reason, they're bunched in with arrays in the AST. We just need to check for a null length and make sure we're inside a slice. By the way, if you aren't familiar with Odin, you might not know why we duplicate the same code for all 3 cases. Basically, when we have exactly one type in a case for a type switch, we get a sort of type narrowing where it will cast down for us. As soon as we have more than one type in the case, we lose that, since even if all the types have the element field, they don't have the same layout, so Odin can't magically make the same code work for all of them. Even if they did have the same layout, though, Odin probably wouldn't allow it, since one of Odin's principles is that types really matter. That's why it doesn't have a lot of implicit casts, even when it would be safe, like an I32 to an I64. So, let's implement that error printing procedure next. You'll notice that we accepted the entire AST node and not just the name. The reason for that is because AST nodes store their position, so we can get nice printing of the error's actual position. That's enough to get us exactly what we need for this demo. It's basic for sure, but in under 100 lines, we're parsing Odin code into an AST, walking that AST, parsing custom attributes, and emitting custom errors. You could take this a ton further though. I showed you how to parse declarations with custom attributes, so you could modify this code to do something like automatically generating shader code for certain types, or you could attach an attribute to procedure to generate Lua bindings, or so much more. If that sounds like something you do want to try out, the source code is in the description as always. If you liked this video, you should subscribe. I've got a few more videos in the pipeline right now about things like creating your own programming language and structuring real large problems in a procedural style. Like this video if you want to help my channel grow, and leave a comment with any questions or suggestions. Also, YouTube keeps telling me about hypes. I don't really know what they are, but if there's like a hype button on your screen, maybe press it. It'd help me, I think. I'm 80% sure it would help me.